Good evening. My name is Martin Tovar, and I'm going to talk about eddy currents that are created when there's a change in electromagnetic fields. Eddy currents are electrical loop currents that are induced in conductors when there is a changing magnetic field on the conductor. This is represented by Faraday's law of induction, which stands that an electromotive force is equal to the change of minus the magnetic flux on the surface in function of time. Eddy current is equal to this electromotive force divided to the resistance of the conductor. A simpler way to explain eddy current is with this picture. If an electromagnetic field, in this case the one created with the coil, gets near the conductor, an eddy current, which can be seen on figure B on red, will be induced, and this current will create a magnetic field as well, as it can be seen on figure C. To show how an eddy current can work, I'm going to use a wireless charger, a homemade coil, and a LED. The wireless charger inside has a coil like this. This coil will be the primary, and usually phones have a secondary over here in order to capture the eddy current. But how this works? Here we have this coil. This coil will create a magnetic field in this way, and this will create an inducted current on the coil, as you can see right now. So right now I'm going to put the coil on top of this, and it's going to create a magnetic field, which will induce a current in this coil. If this coil will be flat, it will work better. Right now, it's blinking because this wireless charger is sending a pulse. It's not sending a constant current because it's not feeling there is a phone. First, I want to show how magnetic field can be seen that it gets weaker. For example, if I put this further away, it will start to blink with less magnitude. To make this work properly, we need a higher load. In this case, it will be my phone. So right now, I'm charging my phone, and it is sending a constant output. If I put here the coil, you can see that the LED was turning on constantly until it feels there's no phone and it starts sending pulses again. So a cool experiment in which we show how eddy currents in magnetic fields make a neodymium magnet fall lower than it should. In this experiment, the electromotive force is created by the magnet falling, and the magnitude of the current depends on the resistance of the conductor. If more foil paper is put around, the resistivity will decrease. Another way to increase the eddy current is to use a bigger rounder magnet that gets closer to the aluminum foil, which will create even more electromotive force. This is the principle of superconductors, the one I will talk to you in a second. It can be seen inversely as well. In this video, an electromagnetic field is created with 120 volts. This repels the coil and makes it fly through a room, as we can see. In this specific video, the current draw was 36 amps, and it dims this guy's house light. So, don't try it at home. This repulsion can be controlled with a voltage, as it can be seen. The lower the voltage, the lower the levitation of the coil. So basically, this is an electromagnetic voltmeter that draws 10 amps. So not the best idea, but it's a cool way to see it. When the resistance is equal to zero, as the case of superconductors, this will create an infinite eddy current that will create an infinite magnetic force. But this is not possible, and this doesn't happen. The only explanation for this is that the electromotive force, also known as minus magnetic flux rate over time, is zero. And this is why superconductors lock to magnets, because their magnetic field will always oppose to any change. So, when the magnet moves, the superconductor moves as well and changes its direction if necessary. This is a really cool effect of electromagnetism. This literally is cool because the temperatures for this are really cold. In this example, the temperature of the conductor is around minus 200 degrees Celsius. Thanks for watching, and I hope you enjoyed the video and learned something new. I will leave the links to the videos used in the description. And once again, thanks for watching.